Well, now I would like to give just a general definition what would mean that the family of operators admit homogenization. Probably in this audience everybody knows, but still let me to be consistent with all the techniques which will be explained. I would like to give the definition of homogenization. So we have a family of operators which are, for simplicity, which are non-negative. In fact, we can assume that they are bounded from below by some in spectral space by some constant, but let's assume that they are epsilon is the family of operators. Non-negative. Let me write it even in the another form, such that m minus L epsilon power minus 1 is well defined. So resolvent is well defined as a bounded operator in L2. We will work on L2. L2 might be in the whole space, or later on we will work in a bounded domain. I don't want to specify. I just say is well defined in L2, and I don't want to specify more. In fact, instead of L2, we can consider even more generic Banach space. It doesn't matter. The definition is rather general. I formulated it slightly adapted to our framework. Is well defined. We say that this family
what m?
Is well defined in L2 for some m from R. In fact, usually we assume that it's well defined for some m and for all larger m. So that's usually there is critical m, after which these operators are well defined. We say that L epsilon admits homogenization if there exists an operator L0 in L2 such that m minus L epsilon f converge to m minus L0 f for any. Yes. Thank you. Minus 1, yeah.
Okay. So does this mean that admits homogenization and strong resolvent convergence is just the same?
Yeah, the same. Yeah, but for homogenization, the word homogenization is related to the fact that we do a particular transformation with operator. This transformation is related to the scaling of the coefficient. So we can define the strong resolvent convergence for any family of operators. If this family is chosen in such a way that it's obtained by just the coefficient scaling, then
I can try to say my own way. Strong resolving convergence holds for homogenization. Correct?
Well, anyway, that's one of the possible definition of homogenization.
For some
For some m, yeah. We can, even for nice elliptic PD, we cannot expect it for all m. As soon as we switch m to the spectrum, inverse operator. Okay. So now I clean, I think, this part. Well, and so far we discussed only the problem defined in the whole space. But for instance, in PD theory, I think even more popular the problem which is stated in a bounded domain, or in some bounded domain strips. Okay, some sets with a boundary. So for local operator, it's clear what Dirichlet condition is or what Neumann condition is. Even Neumann condition is more tricky, but Dirichlet condition is clear. Trace is well defined, so we assume, for instance, homogeneous Dirichlet condition for second order elliptic operator is very clear. The trace on the boundary is well defined. We assume that the trace function is equal to 0. But in a non-local operator, it's not sufficient to say something about the function, behavior of the function at the boundary, because it's just L2 function. In fact, its trace on the boundary is even not defined. So how to impose Dirichlet boundary condition for non-local problem? It's an interesting question. So what we do, we say that so now next problem. So given a smooth, when I say smooth, in fact, Lipschitz is sufficient. Bounded domain. We say that U epsilon is a solution of the Dirichlet problem. L epsilon U epsilon is equal to F in given a small bound Lipschitz domain, let's denote it by Q. In Q, and U epsilon, now the boundary condition is in the whole complement, U is equal to 0, in the whole complement to the set Q. Sorry. If the integral over RD, that's important here, of
before it was minus epsilon plus m on the left.
Well, if you want. In this case, the problem will be uniformly coercive, so m look, for m, for the problem in the whole space, m equal to 0 is forbidden, because 0 is a point of the spectrum. For the Dirichlet problem, 0 is not the problem. I will explain, it's not the problem of the spectrum. So we can choose m equal to 0. But if you want, we can add m. It's not a problem, it's not forbidden. We can add any positive m. And even slightly negative m, it will be okay. But since the best option, of course, always is to choose m equal to 0. So in this case, we choose m equal to 0. And integral over RD, well, maybe, well, a of down to power d plus 2, x minus y over epsilon. It would be easier to write just operator, but well, mu of x over epsilon, y over epsilon, u of epsilon of y minus u epsilon of x dy is equal to f in Q only. We don't care about what happens outside Q. And u epsilon rd minus Q is equal to 0. So we say that u epsilon is a solution if these two relations are fulfilled. Equation. So it's a solution basically in the whole space, but we count only points inside the domain. And this condition, boundary condition, is expressed in this form. So that's the right way to formulate Dirichlet problem for non-local operators. So we'll deal with homogenization of both problem in the whole space and Dirichlet problem.
This is a point-wise definition, right?
Well, here you understand it again in L2 space, if you want, almost everywhere. As usually in L2, we don't care about the set of zero measures, so almost everywhere if you want, yeah. Yeah. In this sense, it's point-wise definition, yes.
The function is extended by 0, but this condition is held only within the domain, right?
Yes. Because, in fact, the right way to understand how the Dirichlet problem looks like is to start with the corresponding variational problem. You take the quadratic form on functions which satisfy this condition, and then clearly when you write down the Euler-Lagrange equation, since we multiply by function which is equal to 0 outside the domain, you don't care about the value of this operator in the complement to the domain.
This definition wouldn't make sense for differential operators, however, I guess. Because if you try to do the same trick, say, for the epsilon over Laplacian,
It works. Why? It works.
well, it only works if you require that u is continuous everywhere. Here you require that delta u is f in q, and never mind what is outside.
No, but when you cross the boundary, you obtain delta function on the surface, right?
Right, but
And in order to kill it, you should care only about the interior of the domain. So you don't care about this delta function which appears outside the.
yeah, I don't care, but then my u is not restricted by zero value on boundary. It can be arbitrary.
Yeah.
Yeah, so this is not the Dirichlet problem for the Laplace separator. That's the point. If you don't care about the delta function, then you do not force your function to be zero on the boundary. You say, it is zero outside the domain. Inside the domain, the equation is satisfied. But if you don't say that it is continuous on the boundary.
I see what you mean. Yeah, I agree. Yeah. Okay, but. But it's non-local operator. Here the picture is opposite. It doesn't care about the set of zero measure, but it will see some layer around the domain, and in this layer plays the role of the boundary. In fact, for instance, if A has a finite support, then we don't care what happens far away. In this case, we don't care about what happens everywhere except for epsilon neighborhood of the boundary. But still, we need some layer of positive measure around the domain to formulate the boundary condition.
I see. So for epsilon greater than zero, everything is safe.
Yeah. Okay, so now, since we are going, in fact, in our approach, we are going to use variational method. I'm going to write down a variational problem for which this equation is the Euler-Lagrange equation. So I think you can guess what variational problem what variational problem is for which the Euler-Lagrangian equation takes this form. So of course we introduce the energy. We will call it E epsilon. E just from energy of U. U is just L2 function, which is equal to double integral over RD. Epsilon to power D plus 2. As well, okay, we should always keep this factor. I often forget it, but then you should add it. A of x minus y over epsilon. In fact, epsilon doesn't play any role for each fixed epsilon. Epsilon now is just a fixed parameter. Mu of x over epsilon, y over epsilon, u of y minus u of x square. 1/2, well, or I prefer to write minus 2 times integral f u over rd. I don't want to have fraction, so that's. After that, we can just divide by 2 the corresponding Euler-Lagrange equation. And now it's a simple exercise to see that it's in the bounded. Well, now we should decide either we work in the whole space or in the bounded domain. In the whole space, let's start with the whole space first. Then no restriction on U, but then we should add
maybe we should also add dx dy somewhere in the integral.
Of course, thank you. Yeah, and here also dx. Well, that's the functional, energy functional, for which you can easily check. It is straightforward exercise to check that what we write here is the Euler-Lagrange equation for this equation. And if we deal with Dirichlet form, then we defined energy. It's for the problem in the whole space. For the problem in the whole space. And for Dirichlet problem, E epsilon of U is equal to integral 1 over epsilon to power d plus 2, the same integral. Let me write just like this. It will be exactly the same, minus 2 times integral fu dx. There is no m here because you remember in the Dirichlet problem m is equal to 0. If u is equal to 0 on rd minus q and plus infinity otherwise. We just penalize the fact that u doesn't belong to the domain by imposing the value plus infinity to this functional. It's preparation for gamma convergence technique. In gamma convergence, usually the function, the fact that the function doesn't belong to the right space or doesn't satisfy some boundary condition, penalized by the value plus infinity for such arguments. That's the way to do it. Well, and
do we need some solid space here?
L2.
Just L2.
L2 because we deal with just bounded operators. It makes a big difference with differential operator. Here, before we pass to the limit, the framework is we deal with the L2 framework, sufficient. After, in fact, we will prove that the family of limiting energy converge to the function which is a function from H1. It will, but it's a quite non-trivial statement. Well, that's the variational problem we are going to deal with because we know that gamma convergence is a very efficient instrument, one of the very efficient instruments in the homogenization theory, and in fact, in stochastic analysis, it's especially efficient because we can use subadditive theorem, which doesn't give us an explicit formula for the effective matrix, but which guarantees the existence and the convergence. The existence of the effective operator gives it its structure and guarantees the convergence. So what we're going to do, in fact, we are going to use this variational functional and to pass to the limit in this functional, and then as a consequence, we will obtain the solution of equation of the corresponding Euler-Lagrange equation, because the Euler-Lagrange equation provides the equation for minimizer of this problem, and gamma convergence under some additional compactness results, which we are going to prove, at least to formulate, it gives the convergence of minimizers also. So if we know the structure of the limit functional, and if we write down the Euler-Lagrange equation for the limit functional, we can guarantee the convergence of solutions of the corresponding equations. That's our plan, how we're going to prove the result.
Just one possible way, right?
One possible way, of course. Of course, in fact, I should mention that there is another way, and in fact, the main reason why we started to deal with this formulation was the problem in perforated domain. Direct methods with non-local condition and the imperforated domain are rather technical. With Elena Zhizhina, we proved this result in the whole space and without perforation for random coefficients, just by using just the corrector technique. But it's the construction of corrector and all the things are really very technical. And if on top of it we want also to have perforation, it's getting really dramatic. So it turns out that in this case, the subadditive theorem reduce a lot the amount of computation and the length of the proof.
Это ваша работа с Андреем Брайтом.
Yeah.
Just
Я скажу, ага.
understand,
Спасибо.
could we not penalize the values outside the domain, but instead assume from the very beginning that U is defined only in the domain and replace all the integrals over RD by integrals over Q? I guess we get the same.
Yes.
Yeah, okay. Just
In this case, yes, it will give the same. But the idea is to deal with this guy and this guy, just to prove just one theorem in the whole space, and then making small modification of these functionals. Use always the same theorem. That's the idea. Of course, you are right. Of course, we can formulate it in a slightly different way. But that's the question. Basically, that's just a question of language.
yeah, sure.
Sorry, but I think in the first integral, it's impossible to change RD to.
No, first integral, the problem is in the whole space. So, of course, here we should have. Yeah, but here, when we work in the bounded domain, here we could. No, why? Here.
Here we cannot actually. Even in the bounded domain.
Here, yeah, you're right. Here we cannot because, look, there are points here
no local interaction.
Wait. No, we can, because here we have. Yeah, there are points where, for instance, u of x is equal to 0, u of y is not. One point is inside, another is outside.
You should still take
Yeah, so we can replace one integral by, but not both of them. If we replace both of them, we will obtain another. Thank you. Yeah, you're absolutely right. Yeah. So it's should be one integral can be replaced, but not both.
So this variational gamma convergence was chosen because it was most promising to go as far as stochastic, right? Yes.
No, okay. Of course, we can obtain the result in periodic case by this method as well.
We are already talking about stochastic.
But we were going about stochastic, and now our next aim is to introduce a stochastic framework. What it means that coefficients are random, statistically homogeneous, ergodic.
Just recap, right? Abstract, general recap, right?
So far, what I said so far, this problem, it didn't assume any structure of the coefficient. Just 6 conditions which were formulated. Till now, we didn't assume any particular form of the coefficient. But now, since we are going to deal with homogenization, we should say something about some translation invariance properties. And it will be statistic homogeneity.
Can I ask another question?
Yes.
So there is a fractional Laplacian, right?
Yes.
Where A is this Reed's kernel, something like that, like 1 over x minus y, and so value power. So can this A be such a Reed's kernel in your case?
We can deal with fractional Laplacian as well, with some coefficient, but it's a totally different theory, because fractional Laplacian is not bounded operator anymore. It's unbounded operator with compact resolvent. So although it's not local, it preserves many properties of differential operator. In particular, its resolvent is compact. And for fractional Laplacian, we start from operator of fractional Laplacian type. In the limit, we have the operator of the same type. It inherits this property from the differential equation.
So this depends on basically on the choice of A. So
Yes, in the case of fractional Laplacian, where we will never have this property, because the kernel is non-integrable. It makes a huge difference.
So the variational problem is to minimize.
Variational problems, yes, variational problems is right. And we can show that the minimum exists. In fact, by convexity, this minimum, it's easy to show that this function is convex. So the minimum exists, minimum is unique. It's okay, it's rather standard. This function is very, very nice and very easy to study, in fact. Strictly convex, yes. Yeah, it's quadratic expression, and with the elliptic part here, everything is strictly convex. The minimum is unique.
You said minimization is over L2RD, right?
Yeah. But so far I cannot pronounce the word homogenization because I didn't formulate the assumptions. So far we don't know if we will have homogenization or not. So I prefer probably to keep these conditions here and to clean this part. So randomness. We assume that we are given a standard probability space, and I use the standard notation for it. space with a dynamical system with an ergodic dynamical system. And I code to x. X is from RD. D-dimensional argument. Sometimes people say D-dimensional time, but I don't like this name. What it is? Okay, I think to. Well, probability space is standard thing, some set, sigma algebra of its subset and probability measure. And what is tau x? Tau x is a collection of measurable map from omega into its. So tau x is a measurable map, okay, omega to omega, such that the following three conditions are satisfied. First, it's a group, so tau x plus y is equal to x to y, and tau 0 is equal to identical map. The second one is the property to preserve measure P for any tau probability of tau x of A is equal to probability of A for any O A from F. And the last condition, which is in fact very important, is measurability with respect to the pair. If we consider tau as a map from RD times omega to omega, omega, it's measurable, is measurable. We should define sigma algebra in this space. We consider Borel sigma algebra here, F here, take the product sigma algebra, and we assume that this map is measurable with respect to this both variables, yeah, to the pair, yeah. So,
which is of these property means ergodicity?
So no ergodicity. That's the property of dynamical system. And addition, we assume ergodicity. We say that tau x is ergodic, and I will define it somewhere. Sigma algebra. But it's sigma algebra. We don't care about the measure here, only the measurability. So it should be measurable. In RD, we consider Borel sigma algebra. Lebesgue sigma algebra sometimes is dangerous in probability theory. So we prefer to deal with Borel sigma algebra. Yes. In omega, we don't have, since omega is absolutely abstract space, we don't have any other sigma algebra except for F script. But in RD, we can consider Borel, Lebesgue sigma algebra. I prefer to deal with Borel. Well, there are two arguments. I didn't want to write X here, because there are two arguments, omega and, if you want, like this. So it, no. X, one argument is here, another argument is here. Then we have map from RD times omega. Definition, I think we say it in this form, tau is ergodic if any set A from F which is invariant with respect to when I write this, it means it is invariant with respect to x for all x, has measure 0 or 1. I can write it like this: P of A times 1 minus P of A is equal to 0. Thank you. And I still have 5 minutes, and I would like to explain. Well, first I give the definition of statistically homogeneous field. We say, now very important definition, because from now on it will be used everywhere. So we say, we are given some random field, which means that the function of two arguments, x and omega, with values in R1, then it's random variable, in RD, then in random vector, and in some Banach space, fixed Banach space, which then it's random function, we don't care, it's random something, random vector, random variable, random, it just depends on the structure of the image space, we don't care. So for simplicity, let's speak about random variables, but the definition will be the same for random vectors, functions, whatever. We say that, or random vectors, since we are going to deal with some matrices, vectors sometimes, then the random variable is a particular case. We say that random vector, let's call it, say, h of x omega, is statistically homogeneous I know the way to write it, process. Random process, it might be a collection of random variables, of random vectors, random functions. Is statistically homogeneous if there exists h tilde of omega only, the random function in omega with values in R1, RD, in the same space, such that, measurable of course, such that h of x omega is equal to h tilde of t to x omega. So if the dependence on x can be expressed in terms of the argument of action of our dynamical system τ, then we say that the random variable is statistically homogeneous. Usually in one-dimensional case, people say stationary. Stationarity and statistical homogeneity is the same thing. Stationarity is usually applies for one-dimensional case. Statistical homogeneity, this term is usually, these words are usually used for multi-dimensional case. In fact, it's the same thing. I don't even know why. Process, random field, process field. Yeah, process are usually also one-dimensional. Yeah, there is a zoo with terminology in this field, so But I hope it's clear. And now you can ask me, still I have 1 minute, I hope. I want to explain. The classical definition of stationarity or statistical homogeneity is totally different. We say that the process is stationary if the following, if it has the following property. We consider arbitrary finite number of points, take the value of the process at these points, take the finite dimensional, corresponding finite dimensional distribution, the law, then we shift these points with the same vector, consider new finite dimensional distribution, and this law should coincide. And now you can say, why do, you can ask me, why do we change the definition of the stationarity of statistical homogeneity? The answer is, there were a collection of works by Dub, who proved that under natural condition, natural measurability condition, if we have some process which is stationary in the classical sense, then probably by increasing the probability space, at the price of increasing the probability space, we can construct on this slightly increased probability space a new dynamical system in such a way that finite dimensional distribution of the process realized in this term coincide with the finite dimensional distribution of the original process. So from the metric point of view, these two definitions are equivalent.
So the converse is also true.
Converse is also, it in both directions. So in one direction, it's unconditional. In another direction, we need some minimal measurability, which is always here, because otherwise we cannot define realization. If we don't have measurability, realization are not well defined, and then it's not clear what we are speaking about.
Any textbook on homogenization where this is explained properly or just explained? Because Zhikov just formulates, right? Let's define first part, right, in terms of dynamical systems.
Good question, because, well, I saw... Yes, I'm afraid, yeah. I think in the Russian version of Zhikov Kozlov-Oleinik book, there are some explanation about this, but in English book,
It was withdrawn.
it was withdrawn, yeah.